Hello and welcome to MyScience Tutorials. In today's video we are back with a brand new topic, which is Ohm's law. So in today's video we are going to be looking at Ohm's law and the combination of resistors, whether in parallel or in series, and how to solve examples on direct current using Ohm's law. So without wasting you guys your time, let's get started. So what is Ohm's law? Now, according to Ohm's law, okay, the current passing through a conductor, okay, is directly proportional to the applied potential difference. So according to the observation of Ohm's, he discovered that whenever we applied a voltage across let's say a circuit, okay, the voltage is proportional to the current passing through the conductors. Okay, now if you are well into mathematics, you know whenever we have a proportionality sign and we remove the proportionality sign, we tend to introduce a constant. So in this example, in the case of Ohm's law, whenever we remove the proportionality sign, the constant that we introduce over here is called R, which is what? The resistance, okay, which can either be offered by the wire or maybe an external resistor in the circuit. Okay, so so we have V is equal to what? IR, where V is what? The voltage or the EMF in some instances, then the I is the current, and then the R, as I explained earlier on, is the resistance. Okay, so according to Ohm's law, we have the voltage is equal to the multiplication of the current times the resistance. This is what Ohms is telling us. Now, before we can be able to move on to solve problems using the Ohm's law, we need to look at some instances where we have some series of combinations. So assuming we have a resistor, okay, and they are connected in either parallel, okay, or they are connected in series, how do we get the overall what? Total resistance before we use it in the Ohm's law to get either the voltage or the current? So this is really important, and then we need to go through that. So let me get some space over here quickly. All right, so let's look at resistors in series. So resistors in series. Now in series, let's say this is our first resistor, our second resistor, and then our third resistor. Okay, now in series we have R1 resistor 1, resistor 2, resistor 3. Okay, so in series we need to take note of some facts. That is, the current passing through the resistors, okay, in a series, the current is the same. Okay, so the current passing through over here, the I, is equal to the current passing through the resistor 1, is equal to the current passing through the resistor 2, the same as the current passing through the resistor 3. So our I is equal to what? I1 is equal to what? I2, which is also equal to what? I3. Okay, so the same current passes through the resistors in series. Now for the voltage is split over the resistors. Okay, so to get the overall voltage, okay, we tend to add the voltage on the first resistor plus the voltage on the second resistor plus the voltage on the third resistor. Assuming we have 4, 5 resistors, we need to add the separate voltages to get the overall voltage of the resistor or overall voltage in the circuit. Okay, now if we now know Ohm's law is V is equal to IR, and then we know in series we have the same current passing through and then the same voltage passing through, what then do we do? Now let's look at how we can find the resistors, okay, how to get the total resistor using these two assumptions. So using assumption 2, okay, or using equation 2 over here, okay, let me use this side. We have V is equal to what? V1 plus what? V2 plus what? V3. And we know from Ohm's law, okay, we know from Ohm's law that V is equal to what? IR, which we have over here. Okay, so we have IR is equal to what? I1 R1 plus I2 R2 plus I3 R3. But from equation 1, okay, we know that what I is equal to what I1 is equal to what I2 is equal to what I3. Okay, so in place of I1, I2, I3, we can use I for all of them. So we have IR is equal to what IR1 plus IR2 plus IR3. But then we have the same I all out, so we can factorize the I out, and then we have what R1 plus R2 plus R3. Okay, but then again we can see that the I over here, which is the current over here, is the same as the current passing through over here. Okay, so they are both the same, so they can cancel out, or we divide both sides by the what, the I. So we will be having the total resistance, which is R, to be equal to what R1 plus R2 plus R3. So whenever you have a circuit and then you have your resistors in series, the overall resistance, okay, of the resistors you have is the sum of the individual resistance of the resistors. Okay, so your R will be what, or your R total will be equal to what R1 plus R2 plus R3. So this formula is very, very important, so let's take note of it. It will come in handy when we are solving problems on Ohm's law, on a circuit using Ohm's law. So let's have a look at the second scenario when we have the resistors connected in parallel. Okay, oops, let me quickly get rid of everything here. Okay, so whenever we have resistors in parallel, okay, which means we have something like this. One resistor is over here, then we have another one in the middle, and we have the final one over here, all connected, and then we have our current flowing through. Now in parallel, okay, what happens is that the current flowing through the circuit, okay, is split over the resistance, the resistors we have over here. Okay, so the current is not the same current that flows through. The current that flows through resistor 1 over here, R1, is different from the current that passes through resistor 2 and then resistor 3. Okay, so to get the overall current that passes through all of them, okay, which is, let me use IT as the total current. Okay, we add the first current that passes through the resistor 1 plus the current that passes through the resistor 2 and then the current that passes through resistor 3. Now the second assumption we can get from the parallel connection is the fact that the voltage applied through the circuit, okay, the voltage is the same across the resistors. Okay, so the overall voltage is the same as the voltage that passes through the resistor 1. It's also equal to the same voltage that passes through resistor 2, and then the same voltage passes through resistor 3. So this is our equation 2. Now if this is the case, then we can now derive an expression for how to get the total resistance of the resistors we have in the circuit if we have them connected in parallel. So let's use equation 1. So we have our I total, which is the total current, to be I1 plus I2 plus I3. Now this is beautiful. From Ohm's law, we know V is equal to IR. So if we make I the subject over here, okay, our I will be equal to what? Voltage over resistance. Okay, so it means over here, instead of having IT, we have VT, the total voltage over what? The total resistance RT is equal to what? V over R1, which is V1, plus V2 over R2 plus V3 over R3. Now if this is the case, okay, and then we know that from the second assumption we have over here, okay, the total voltage, okay, V total, but V total is equal to what? V1, which is equal to V2, which is equal to what? V3. So in place of V1, V2, V3, we can put V total over there. So we have what? V total over what? RT is equal to what? V total over R1 plus V total over R2 plus what? V total over what? R3. Now we factorize out the V total, okay? So we will have V total into bracket 1 over R total, okay? This is the same as what we have over here. Is equal to what? V total into bracket 1 over what? R1 plus 1 over R2 plus 1 over R3. Okay, so from here we can cancel out the V totals that we have, and then we get to realize that the overall resistance, okay, when we have the resistors connected in parallel, is given by what? 1 over RT, which is the total resistance, is equal to 1 over the sum, the inverse of the sum of the resistors, so 1 over R1 plus 1 over R2 plus 1 over R3. So this is how we use Ohm's law and this simple assumptions that we made over here to derive an expression for the total resistance in a circuit. Okay, so let's move on. So let's also take note of this, and then let's take note of how to get the total resistance in case we have the resistors connected in series. Now let's look at something else. We have something we call internal resistance. Internal resistance. Now what is internal resistance? Now internal resistance is the resistance offered by a cell, okay, within a circuit. Okay, so whenever we have a cell in a circuit, sometimes they tend to offer some resistance to the flow of current through the circuit. Okay, so this internal resistance is represented with small r. Okay, and then let's look at how we derive an expression for that. So whenever we have an internal resistance, okay, then the total resistance of that particular circuit becomes what? The R total becomes what? The resistor, in case we have a resistor over there, the resistance of that resistor plus the internal resistance of the cell. Okay, so this is what we get as the total. Now mind you, if you have the resistors in series or in parallel, you need to, like, the R over here will not just be 1 R. If it is in series, you add the R's, R1 plus R2 plus R3 before you add the internal resistance. If it is in parallel, you add 1 over R1 plus 1 over R2 plus 1 over R3 before you add your internal resistance. Okay, so from here the EMF or the voltage, the EMF, okay, which is represented with E, or we can say the voltage. Okay, so normally with internal resistance they tend to say EMF instead of voltage. So the EMF is given by, just like Ohm's law, is IR. Okay, now R total, now the EMF is equal to, now the total resistance over here, okay, is equal to what? R plus small r. Okay, so we have the current into bracket R plus small r. So our EMF is equal to what? Current times R plus I small r. Now we know from Ohm's law that V is equal to IR. Okay, so the EMF, okay, the EMF is equal to what? The voltage, okay, plus what? IR. Okay, now let's look at something interesting. So the relationship between the EMF of a cell and then the voltage of the cell is the fact that EMF of a cell is equal to what? V plus IR. Now what is this IR? The I and then the small r. The I and then the small r is called what? The lost voltage. Okay, so whenever we have current multiplied by the internal resistance offered by a cell, the whatever we get is called the lost voltage. Okay, so the EMF of a cell is equal to what? The voltage plus the lost voltage. Okay, so that we get a voltage plus the lost voltage. So this is the relationship between EMF of a cell, the voltage, and then the lost voltage. Okay, so in case you are asked to find the lost voltage, okay, all you need to do is to get the current that is flowing through the circuit, and then you multiply it with what the internal resistance, and then you get your loss voltage. Now if we all understood everything that I've explained so far, then let's have a look at some few examples to enhance our understanding of the concept Ohm's law. So yeah, so let's look at example number 1. So in example number 1, let's write solution over here. Okay, so we have a cell offering a voltage of 6 volts, and then it has an internal resistance of 0.5 ohms. Then we have an external resistor which is giving us 0.2 ohms over here. Okay, and then we have the current flowing in this direction. So from here straight away we can say the EMF over here, the EMF, this is the EMF offered by the cell. The EMF is equal to 6 volts. Okay, so the EMF, we know EMF is equal to what? Current, okay, times into brackets R, which is the total resistance of the cell, plus the small r. Okay, now the EMF in this example is 6 volts, so we write 6 is equal to, we don't know the current, that is what we are looking for, so we have I. And then the resistance offered by this resistor is 2.5 ohms, so it's 2.5, plus the internal resistance of the cell is what? 0.5 ohms. Okay, so we have 6 is equal to, now this is what? 3. So we divide both sides by 3, then we get our current to be what? 2 amperes. Okay, so in this example the current flowing through this circuit is what? 2 amperes. Beautiful. Let's have a look at the second example. So let me write here solution. Now in the second example we have 2 resistors and they are connected in series. Okay, so let's look at all that we have. We have our voltage source is equal to 2 volts, and then we have our current passing through, but then we don't know our current. We know the resistance of the 2 resistors we have over here. So we know V from Ohm's law, V is equal to IR. Okay, now the resistor we have over here, they are connected in series, so the R total, okay, will be equal to what? The sum of the first resistor plus the resistance of the second resistor. Okay, so it will be 1 plus 1, which is equal to what? 2 ohms. Okay, now from here we know that 2 volts, okay, is equal to what? The current we don't know, times what? 2 ohms, which is the resistance we have over here. Okay, so we divide all by 2. Okay, this is I. Okay, so we get 1. Okay, so our current in this example is what? 1 ampere. Okay, so let's have a look at the third example over here. Okay, so the third example we are looking at the EMF. Okay, is giving us 10 volts. We don't know the current. We have 2 resistors connected in parallel, then we have an internal resistance offered by the cell. Okay, so in this example we have the solution. Okay, we know the total resistance, okay, in the cell will be what? The total resistance of the resistors we have over here plus the internal resistor. Okay, the resistance offered by internal the cell. Okay, so this one, they are connected in what? Parallel. Okay, so the RR over here will be what? 1 over 2 plus 1 over 4, and this is giving us, let me quickly punch that. So we have 1 over 2 plus 1 over 4, and this is giving us what? 3 over 4. So our resistance over here is 3 over 4. That is for just these 2. Okay, so the R total in this example is what? 3 over 4 plus 0.5. Okay, and this will give us plus 0.5 will give us 5 over 4, or 1.25 ohms. Okay, so this is the total resistance that is flowing through this whole circuit. Okay, so from here we know that what? Our voltage, or the EMF, V, is equal to IR. So I is equal to what? Voltage over resistance, which in this example will be what? 10 divided by 1.25, and this will give us 10 divided by 1.25. So this is equal to what? 8 amperes. Okay, so the current passing through this whole circuit is what? 8 amperes. Okay, so this is how we solve examples of direct current questions using Ohm's law. And then hello and welcome to MyScience Tutorials. In today's video we are going to be looking at Kirchoffs Law, and then how to use Kirchoffs Law in calculating in solving practical examples of an electrical circuit. So without wasting much time, let's get started. Now Kirchoff has two laws that we normally use in direct current, that is calculating the amount of current that flows through a circuit when we have multiple resistors and then multiple source of EMF, or our applied potential. Now the first law, which is okay, which is normally called the conservation of energy, the law of what? Conservation of charge, conservation of charge. Okay, this law states that, okay, the sum of currents arriving at a junction in an electrical network is equal to what? The sum of the current leaving the junction, or the algebraic sum of currents at a junction of a circuit is 0. What do we mean by this? Okay, so the law is telling us what? The sum of current arriving at a junction is equal to what? The sum of the current leaving the junction. So we have an electrical network in this form. Let's say we have wires connected this way. Okay, so the wire came down like this, and then it has been split, it has been divided into two. Okay, so this is the junction that we are talking about. Okay, so this is our junction. Let me use another color for that. So this point, okay, is what we are calling the junction. Okay, so when we have current I coming over here, okay, then we have I1 leaving in this direction, and then we have what? I2 leaving in this direction. Okay, what Kirchoff wants to tell us in the first law is what? The sum of the current arriving at the junction, that is, if you see the arrow, it means this current is now arriving at this junction. Okay, so the sum of the current arriving at the junction, which is I, should be equal to what? The sum of the currents leaving the junction. Okay, so this is the junction, so the currents leaving the junction in this example are what? I1 and I2. So this means I1 plus I2 should be equal to what? I, which is the current arriving at this junction, which means the current arriving over here will be split into two, not two equal parts. Okay, that doesn't mean if we have, let's say, 4 amperes coming here, 2 amperes will move this way and then 2 amperes will move this way. No, that is not the case. Okay, so we may have 4 amperes arriving at the junction over here, but then we may have 0.5 amperes passing this way and then 3.5 amperes going this way. Okay, it is not fixed. Okay, so never say it is the sum of current arriving, okay, is equal to what? Half the sum of the current leaving. No, that is not the case. Okay, now the second one is telling us what? The algebraic sum of the current at a junction is equal to what? 0. Okay, so which means if we rewrite this very well, okay, so I, then if we bring this to the other side of the equal to sign, we have minus into bracket what? I1 plus I2 is equal to what? 0, which means the current at this particular junction is 0, because the one that is arriving is the one that is being split into two. So at this junction there is no current at all, or the current arriving is equal to what? The sum of the currents leaving that particular junction. So this is what the first law of Kirchoff is telling us, which is what we call what? The conservation of charge law. Now the second law of Kirchoff okay, so the second law is what? The law that is not conservation of charge. All right, let me just get rid of everything here. Okay, so the second law of Kirchhoff is telling us what? It states that in a closed loop of electrical network, the algebraic sum of the what EMFs is equal to the algebraic sum of the potential difference. Okay, let me take that again. It states that what? In a closed loop of an electrical network, the algebraic sum of the EMFs is equal to the algebraic sum of the potential differences. So it means when we have a closed loop, this only applies to closed loops. So if we have closed loops in this way, okay, then we have our source of EMF over here, then we have our resistors connected over here, another resistor over here, then we have another one over here. So this is resistor 1 R1, this is resistor 3, this is resistor 2. Let's name here A, B, C, and D. Alright, so Kirchhoff is telling us, okay, what is trying to say in this second one is that the total EMF over here, so the EMF over here, okay, is the sum of the various potential differences over these resistors or loads over here, which means that when the EMFs, the I, okay, when the EMFs moves from here and it comes over here, okay, the potential difference over here will be different from the potential difference on this resistor, which will also be different from the potential difference we have over here. Okay, so it means the EMF, the overall EMF is what? The sum of the potential difference 1 over here plus the potential difference 2, the second potential difference which is this, okay, then plus the third potential difference. So if we add the various potential differences over across these loads, which are the 3 resistors we have over here, that should give us the overall sum of the EMF that we have. And then what is the potential difference that we are talking about over? This is simply just the product of what? Current times resistance, or what? Volt. Okay, so it means when this current pass through this particular one, okay, we multiply the current and then the resistance, then we get the potential difference over this load. Then the current that will pass through here, we multiply that current with the resistor 3, then we get the potential difference on resistor 3. The same way, the current that will pass through this resistor 2, we multiply the current and then the resistance of this resistor 2, then we get the potential difference 2. So once we add all these potential differences, we should get the EMF of the cell. Now if this is what Kirchhoff is telling us, let's have a look at a practical example of how to use these two laws to solve a problem on Kirchoffs law. Okay, so let me quickly draw a diagram over here. I know this is very ugly, but let's just manage it. Okay, so we have 4 volts over here. Then at this side we have 2 volts over here. We have this resistor, okay, 1 ohms. We have another resistor, 5 ohms, and we have this one, 3 ohms over here. Then luckily for us, they are telling us I is over here, okay, and we have I1 moving in this direction, then we have I2 moving in this direction, okay, and then they are labeling here A, B, C, D, E, and then F. Okay, so the question is telling us to calculate the current. Okay, 1, find the current I in this example, and then 2, the potential difference. Okay, the potential difference across what? B, E. So this is the question that we are being given to solve. So before we go on ahead, okay, let's define some terms. So let's say let what? E1 be equal to what? The 2 volts. Okay, so we are saying EMF 1 should mean the EMF that we are having over here. Okay, so E2 should be equal to what? 4 volts. Then let's say R1 should be equal to the resistor 1 over here, which is the 1 ohm resistor. Then we are saying what? R2 should be the 5 ohm resistor we have over here, 5 ohms. Then R3 should be what? The 3 ohm resistor that we have over here. Now if that is the case, we also need to take note of the fact that what? The sum of the current arriving at this junction, okay, the current passing through this resistor arriving at this junction is being split into 2 over here. So we have what? I is equal to what? I1 plus I2. Let's name this equation 1. This is really important. So now that we have that, let's look at how to solve this problem. So let's consider loop A, B, E, F, A. So we have A, B, E, F, A. That is A, B, E, F, A. That is a closed loop. Okay, so in a closed loop, we are saying what? The EMF is equal to what? The sum of the potential differences. Okay, like I said, so the potential difference across this particular 2 resistors is what we are going to add. So in this example, the potential difference across the 5 ohm resistor over here is what? Is I times what? 5. Okay, that is current times the resistance, okay, to give us the potential difference. Plus we can see that the I1 is the current that will go and pass through the 1 ohm resistor, not the I, because the I is starting from here. Okay, so it's flowing through the 5 ohm resistor. Okay, so it means the I1 will now flow through what? The 1 ohm resistor. Now the EMF that we have in this closed loop, that is A, B, E, F, A, is what? 2 volts. So we have 2 is equal to, now the I from equation 1 is telling us what? I1 plus I2. So we have here I1 plus I2, that is for the I, times 5 plus what? I1. Then we now break this down. So we have 5I1 plus what? 5I2 plus I1. So we have 2 is equal to what? 6I1 plus 5I2. Okay, so let's quickly make what? I1 the subject over here. So making I1 the subject, we have what? We send this over to the equal to sign. So we have 2 minus 5I2 then divided by 6 as our equation 2. So this is what we have for our equation 2. Now let's have a look at what we will have for let's consider the second loop and see and get the third equation, so that we can solve them simultaneously and get our answer. So I believe at this point I can get rid of the question and everything over here. So if you've not copied it so far, copy it somewhere, because I'll be taking them off right now in a second. So all right, I hope we are all done copying that. Okay, so I know that is very bad, but then, so if we consider the second loop, okay, considering loop, okay, B, E, D, C, B, okay, which technically, let me draw it something very small. Okay, let me redraw everything so that we can all be on the same page. So we have the 4 volt over here, then we have 2 volt over here, we have 1 ohms over here, we have 5 ohms over here, then we have the 3 ohms over here. So this is A, B, C, D, E, and F. So we have I1, I2, and then we have I. Alright, so considering loop B, E, D, C, B, if we consider this closed loop, the EMF, okay, by the second law, the EMF is equal to what? The potential differences. So the EMF over here is what? 4 is equal to, now the first potential difference will be this one, and then the second potential difference will be this one. So we have what? I times 5 again, then plus, in this second loop, we have the I2 is the current that is flowing through the load over here, or the resistor over here. So we have what? Plus what? plus 3 into bracket I2. Okay, but then we said earlier on that what I is equal to what I1 plus I2. Okay, so that is the equation 1 we had, so let's input it here. So we have 4 is equal to what I1 plus what I2 multiplied by 5 plus 3 I2. So 4 is going to give us what? This is 5I1 plus 5I2 plus what? 3I2. So 4 will give us what? 8. This is 3I2. So we give us 8I2 plus what? 5I1. This is equation 3. Okay, so if we have all equation 1 and equation 2 written down somewhere, let's now go ahead and input the value of what I1, which is the equation 2, into equation 3 and see what we will get for our current. So let me get rid of everything over here, including equation 2. Okay, so this is 8I2 plus 5I1. Now putting equation 2 into equation 3, it means we'll be having what? We'll be having 4 is equal to what? 8I2 plus 5 into bracket I1 we had was what? 2 minus 5I2 divided by 6. Okay, so if we use the 5 to multiply everything over here, we get what? 4 is equal to what? 8I2 plus this is 10 minus what? 5 times 5 will give us 25. So 25I2 divided by 6. So let's multiply through with the LCM, which is 6, to get rid of the fraction over here. So 6 times 4 will give us what? 24 is equal to what? 6 times 8 will give us what? 48I2. Now plus 6 times the whole of this fraction will still give us what? 10 minus what? 25I2. So this means we can bring the 10 over here. So we have 24 minus 10 is equal to 48I2 minus 25I2. So this means we have 14 is equal to what? 23I2. So we divide both sides by 23. Okay, so we have our I2 to be equal to what? 0.61 ampere. Okay, so our I2 is what? 0.61 amperes. Now if that holds true, if that is our value for I2, then let's try and get I1 so that we can combine I1 with I2 so that we can get our I, which is what the question is demanding that we find. So from here we know what I1 from the equation number 2 we had I1 is equal to what? 2 minus 5 I2 divided by 6. So this means we have 2 minus what? 5 into bracket 0.61 divided by 6, and if we punch this into the calculator, we are going to get negative 0.175. So which means our current I, which is what? I1 plus what? I2 will give us what? 0.61 minus 0.175, and this is giving us what? 0.435. So it means our current I, which is flowing through the circuit over here, which is what the question is asking us to find, is what? 0.435 amperes. Okay, let's include the unit for the current. So it's 0.435 amperes. Now the second aspect of the question is asking us to find the potential difference across what? The potential difference across BE. Now the potential difference across what? B and E, okay, is just the product of the current, which is I, times what? R, which is the resistance over here. Okay, that is the potential difference, okay, across BE. So the potential difference across what? BE is equal to what? The current, which is what we found over here, 0.435 times the resistance, which is 5. So if you multiply this, we are going to get what? 2.175 volts. So this is the potential difference across what? B and E. So yeah guys, this is all I have for you in this video. Thank you so much for watching, and I believe this actually helps you solve more questions on Kirchoffs law and how to tackle problems involving such more complex circuits diagram, unlike the normal ones that we are used to. So thank you so much for watching, and then I'll see you in the next video. Bye bye.